In this video I want to talk about example 1 from the FDWK book, chapter 3, section 4. What we have in this problem is an enlarging circle, and we want to find the rate of change of the area of the circle with respect to its radius. And maybe the easiest way to do this would be to look at a table. If we had a picture to look at, it would also be very explanatory. But I'm going to open up the graphing calculator. And I'm going to go into y1 and I'm going to put in the area of a circle, which would be pi r squared. And in this case we'll use x instead of r. Then what I'm going to do is show a table of values as r changes. And so I go to table set and I start the table at 1 and delta table will be 1, and I'm going to change independent to auto. And now if I go over to look at a table of values, you can see now that as the radius increases, the area obviously is also increasing, but the area is not increasing at a constant rate. So for example, when the radius is 1, when it goes from 1 to 2, we got an increase of 3.1416 to 12.566. So roughly an increase of 9.4 whatever. But when we go from radius equals 2 to radius equals 3, we have an increase of 12.566 to 28.274, which is now an increase of roughly 16. So the rate at which the area is increasing as the radius increases is a function of where the radius is. So I hope that's clear. I'll say that again. The rate at which the area increases, the rate at which the area of the circle increases is a function of the radius. Obviously, the area of the circle is a function of the radius, but the rate at which the area is increasing as the radius goes up by 1 is also a function of what the radius value is when we're checking the increase in the radius. So for part A, what we want to do is to first of all write the area of a circle. And of course we know that that's pi r squared. Then we want to find the rate of change of the area of a circle with respect to its radius. And so what we want to do is we want to find ddr. That means the rate of change of something with respect to radius. And so we take the rate of change of the area with respect to radius, and that's the rate of change of pi r squared with respect to radius. And so that would be dA dr is equal to 2 pi r. And so that's an interesting phenomenon because it's saying that the rate at which the area of the circle increases as the radius increases is equal to the circumference of the circle. And let's try to make some sense of that. So we have this circle here. What we want to say is that as the radius increases by an infinitesimal amount, and so we have a radii there, and we want to increase it by an infinitesimal amount. And actually, what the derivative really means there is that as the radius changes by 1 unit, how much do we expect the area of the circle to change by? When the independent variable changes by 1 unit, how much will the dependent variable change by? And that's why we call it dA dr, the amount of change brought about in the area as a result of a 1 unit change in the radius at a certain point. So we can see what happens is that's actually, we're going to say that that's a 1 unit change in the radius. And so that green circle then gives the increased area as the radius changed by that amount. And you can see that the amount of increase really is just the circumference of the circle at its original point times 1. And so if I were to take that green shaded area and stretch it out as a rectangle of height 1, and so the rectangle would have the area 2 pi r times 1. And that would be the amount of increased area as the radius increases by 1.